everyone, and welcome to your 7th Embedded Systems lecture. So in this lecture, I've discussed that the embedded system is actually the computer that deals with the information that we're acquiring from the environment, and it sends some commands and deals with the environment using different equipment. And in order to hear or sense the environment, we can use a bunch of components here, and we call those components the sensors. But then again, an embedded computer can also get some commands directly from the human users through buttons, keyboards, any other equipment. For example, we've seen in the last lecture, in order to kick the dog, the watchdog timer, we needed to push a button in order to make sure that the system does not reset. And on the opposite side, we can see that we have different components to act on the environment, hence we call them actuators. And those are connected to the outputs of your embedded system, embedded computer. But then again, some information could be provided to the human users through LCDs or LEDs, etc. So we can use actuators that provide information for the users and not directly automated to act on the non-human environments. So this is the schematic that needs to come to your mind whatever you think of embedded systems. So we need the sensors to get it to sense the environment, and these will be connected to the ports programmed as inputs, and then the ports that are programmed as outputs are destined to be connected to the actuators. We're going to dive into details about the different types of sensors and actuators. First thing first, most probably and all of the time to be more accurate, whenever you're going to use a sensor, you surely need to connect it to a couple of things. Can you name them? It's definitely the VCC, the voltage, the power voltage, and then in order to make sure that it is safe, you need to connect it to the ground. The objective of a sensor device is to get the values from the physical world, and those values are by nature analog. And as I told you in my previous lectures, the sensor will send to the microcontroller, or more generally the embedded system, the embedded computer that is connected to, some voltage. So it's always a bunch of ones and zeros, or even sometimes the current, but it doesn't really matter. What I'm trying to say is, for instance, if you're using a temperature sensor, it's not going to spit out directly the temperature as you know it in degrees, or Celsius degrees, or Fahrenheit. Rather, it's going to send voltages, and then you need to apply some kind of equations in order to have the equivalent of the information provided by the sensor in terms of Celsius degrees, or Fahrenheit, or Kelvin, or whatever. Alright, so out there you're gonna find two types of sensors. Can you think of one type that you particularly used in the DSD course with me? Alright, so again, feel free to pause the video, whatever you're attempting to answer my questions before getting the answer. That would be a good exercise for you. So yeah, the types of sensors, out there could be analog ones, and then we can have digital ones. So analog ones are usually spitting out raw voltage, raw data, in the sense of it's not sampled, it's not honed, it is raw. And then, of course, we have the digital ones, and those are usually way much easier to use because the sensor just spits a bunch of ones and zeros, and you have to interpret them within your microcontroller. Alright, so in case of using the analog sensors, so knowing that your embedded computer only understands ones and zeros, so there should be something, some kind of interface in order to get some ones and zeros out of the continuous or the continuum that we have here. This is where an ADC becomes extremely handy, and using a digital sensor you can do away with ADCs because the information is already in ones and zeros. However, usually digital sensors are they have low calculation range, meaning that they are usually less accurate because of the quality of the ADC that is embedded within them, or for different reasons. This is why if you're looking for more accuracy, it's better to get a sensor that spits out raw data here, and then you're gonna deal with the raw data inside your microcontroller using the proper ports that are connected to the ADC, and you can also use some reference voltages using the pin that we tackled early in this course, and of course I'm talking about the AREF pin. So to make a long story short, if you're looking for easiness of setup and the use of sensors, you're gonna go for a digital one, but you will be sacrificing the accuracy or precision. And if you want to go for a better accurate and precise data, you're gonna go with an analog one. However, it will be more complex to implement and use. Alright, so here are some examples of sensors that are out there. Some of them are digital, others are analog. For instance, and this is a game we played in the face-to-face lecture today, is try and guess the different sensors. So here we can see an analog pressure sensor, here a digital pressure sensor, here is a electromagnetic field sensor, here something that we call a load cell, and it is a weight sensor. So you use this one in order to weight some some elements. And I had one bachelor project the last year. It was about a smart food truck system where the students had to use the load cell here to weigh the different food components or ingredients. I was looking for that word. So the different ingredients in order to estimate, for instance, how much time would it take to get a sandwich done, for instance. Here's a temperature sensor. Here you can see a gas sensor. Here you can see a humidity sensor, a moisture sensor as well. So moisture, I had 2 years ago when I arrived here, a student work on a smart planner system where the plant is able to detect whether it's thirsty or not and go to a base to drink water. So he used a moisture sensor in the plant, and hence was able to detect if the moisture is, if the dirt is moist enough for the plant or not, in order to command some actions. And lastly here, what you're seeing is a wind sensor. Alright, so as we've seen for sensors, you can guess there are different types of actuators as well. So go ahead and try to figure it out yourself. Alright, naturally we're gonna go always with the easy. We always start with the easy one. That is the digital actuators. Alright, so a digital output that is connected to an actuator is, an actuator only requires a high or low voltage, meaning that it's either I have 5 volts or 0 volts. 5 volts means that the device is under power, hence it's fully working, or it's connected to 0 volts, hence not operational at all, so it's off, right? You can think of a LED as an example. So when you apply a digital 1 to a LED, it will light up, and if you apply or drive the pin low, it will turn off. Alright, so this is the easy part, and we've seen that we can use digital ports in order to control this type of actuators. What is the other part, or what is the other type? Alright, so imagine that you need an actuator that has more than a non-enough scheme here. So imagine that you need more values to output more values in order to have different states or different operational modes. What can you think of? What type of actuators could be commanded like that? Motors, for sure, because whenever you're driving a motor, it's not about going full speed or stopping. You can have different speeds, different rotational speeds for the motor. And the motors actually that we're gonna see in this class, plus you're gonna use in your project, in your toy car project, are divided into two types. The first one is a servo motor, and the other one is the DC motor. So the DC motor over here is, it's a classical motor in the sense of whenever you're applying some kind of voltage, it will start spinning indefinitely until you cut the voltage. You can drive it with different speeds, so the more voltage you have, the faster it goes. The lower voltages you have, the slower it gets. What about the servo here? So the servo is a motor that only rotates between two different angles. It goes from 0 to 180 degrees. Alright? So you're gonna use both types of motors in your project. One for gas and one for steaming. One for propulsion, to make the toy car run, and the other one is to steer it, to change the direction, to make it avoid obstacles, etc. So which one is used for what? You guessed it right, the DC motor would definitely be used in order to gas up the car, so in order to you know to roll, to drive it, or in reverse. And the servo motor will be used for steering the car. So you can, it's like a steering wheel. You can go rotate between 0 and 180 degrees. We have a problem here though. What is the problem? The problem is, and you need to think about it, is that the actuators are connected to the embedded computer. And the embedded computer, whether it's a microcontroller or something else, it only spits out ones and zeros because it operates with ones and zeros. We need to try to find a way to convert those ones and zeros into some analog control, in the sense of, instead of only having 1 or 0 as an output, we're going to have values between 1 and 0 to represent the different speeds, for instance, or the angle for a servo motor. How can we do that? It is a challenge that we're tackling here. First thing first, let us study in more details the different schematics about the servo, about the motors, and we're going to start with the DC motor first. Here you're seeing a classical Arduino board, and it's an Arduino Uno board, and we're seeing the different connections, and we're going to try and understand the connections. And this is what you'll be doing in your project. You need to hook up your DC motor to your board and make it run. So first things first, we need to hook up the different grounds and the VCC. You can see, you can identify the motor here, the DC motor, the board, and then you are seeing different components here. So the power supply that you're seeing here is used for a reason, especially with motors. What would that reason be? So the reason behind it is the motor might need more voltage than the board can provide, hence it needs an external power supply. However, if we're not going to control this external power supply, this means that whenever we're hooking up our motor, it will go on full speed, and when it's not hooked up, it will not rotate at all. This is why we need to connect it to the board so we can get to control it whenever switching on and off the external power supply. Alright, so in order to do that, we're going to use a transistor here. So the transistor acts like a switch. So it is connected to the grounds, right? And then we have the power supply here. So we can see when the switch is closed, we have a full circuit. And when the switch is open, so this connection here does not exist, well, we're going to see that this circuit is open right here. How does this particular transistor work? So basically we have one leg is connected to the control pin here. So when we apply a 1, we're going to close the circuit between those two, between DNS. And when we apply a 0 here, we're going to open the circuit that is between DNS. However, I'm still having a problem with that, because if I'm applying a 0, alright, so the motor is not working at all because the switch is open. And when I'm applying a 1, it will run on full speed again. How can I deal with that? So let's let it marinate for a second, and we're gonna tackle it. But before tackling it, you can identify here a resistor. This is for safety, so this is a pull down, it's connected to the ground. And you can notice a capacitor here. So the reason behind having a capacitor because supposedly we'll be having different voltages, different voltages for different speeds. So in order to have some kind of cushion, right? So it charges, then it decharges, etc. So the changes will not be abrupt. And the last element that you're seeing here is called a diode, and you can see that it's actually polarized, and it goes from, this is the positive side and this is the negative one, and it's connected in an opposite way, in a parallel opposite way to the DC motor in order to secure the system and do away with the potential kickback of the motor. So without getting into too much details about it, the kickback of the motor is the phenomenon that happens whenever you're applying a voltage to the motor, then you stop it, so it will keep on rotating, generating its own voltage. So in order to secure the injection of that generated voltage back into the system, well, you need to make it happen here. So the diode, it prevents the kickback of the voltage of the motor back to the system. Alright, so let's try and understand how can we control this particular signal here in order to have different speeds, as opposed to a full speed or no rotation at all. Notice the three letters here, we're gonna see them. Servo motors. Alright, generally speaking, and even with different data sheets, you're gonna find that the servo motors have how many wires? 3 wires. So naturally, as I said earlier in the very first slide today, where the sensor or the actuator as well, so any electronic component that you might be using, it necessarily needs power, so it needs to be connected to the voltage, to the ground of course, and then some control signal, remember, because the servo is meant to rotate between two different degrees, let's say 0 and 180 degrees, so we need some kind of signal, right, to indicate the position of the servo. And depending on the signal, we'll be having a servo not rotating at all, rotating at 45 degrees, rotating at 90 degrees, all the way up to 180 degrees. So the question is, what kind of signal do you think we're gonna use here? So if you remember the 3 letters that we've seen in the DC motor, it still applies here. So the 3 letters were PWM, and the signal wire is expecting an input that is a PWM, and PWM is short for pulse width modulator. You can notice 2 things here. Pulse is like a pulse, electric pulse, right? And the width, it has to do with the size of the pulse, or the, it could be tight, or it could be wide. So a pulse is something like that, and then apparently with the PWM we're gonna get to control the width of the pulse. So it could be a short one or a wide one, and you can imagine that a short one will be interpreted like the degree, a small degree here, and the large one could be interpreted as a higher degree, or a wider angle. Alright, so let's get into more details. So we're gonna try and get analog-like results using digital computer, so a bunch of ones and zeros. So let's check this out. So if you remember quite well, on the different ports we can put ones and zeros. So a logical one is usually 5 volts, especially with Arduino boards or Arduino-like boards. And this logical 0 is usually 0 volts. So the idea is to define some kind of frequency, because remember, in electronics everything deals with clocks, hence frequencies. So let's imagine that we're talking about a frequency, and the inverse of a frequency is a period. So we're interested in observing what would happen in a particular period. So it's not about the value itself per se, but I mean it's the different values within a whole period. Fair enough? So let's follow the schematic and see this particular period here. So this is the first period, right? Because of the frequency. This is the second one, third, etc. And how do you know the periods? It's because of the up and down times, remember? So rising edge, falling, and then the next rising edge defines the next period, etc. Alright, so the whole idea is to do what? Now my motor, if I apply a 0 volts to it, well, it won't rotate at all. And if I apply 5 volts to it, it will, if I apply 5 volts to the control, hence, a full power to the motor, it will rotate at full speed. Or in case of a servo motor, it will go all the way up to the 180 degrees. So the idea is to observe the different values on a particular period and then get the sum, the mean of the different values that we're getting. Let me explain it in more details. So let's get the second period here, and we can see we have some uptime and then some downtime. So my signal, we spend some time at logical 1 and some time at logical 0. So if I'm looking at the signal as a whole over a whole period here, we can notice that the total time spent at 1 and 0 added together and divided by 2 will give me the mean value over the whole period. Hence, if I spend half of my period at 5 volts and the second half at 0 volts, this means that all in all over the whole period, it's as if I spent my whole time at 2.5 volts. Alright? Let me get a pen so we can make sure that everyone gets that. So I have my 0, I have my 5 volts. So imagine my period starts here. I'm spending 50% of my time up and 50% of my time down. This means that all in all, as a mean here, it's as if I'm spending all of my time in the period at 2.5 volts. Alright? And bingo. This is exactly what we need to control the different speeds of a motor. So all you have to do is control the uptime and then get the mean in order to have a particular voltage that can vary between the 0, no rotation at all, and whatever the full voltage is, in order to have the highest speed. Fair enough? So the uptime is called the duty cycle, and this is usually a percentage. So you're gonna say, if you're gonna create a PWM signal with 50% duty cycle, this means that 50% of your period you'll be spending it up, and the other 50% you'll be spending it down. This means that as if you spent your whole time at 50% of the whole voltage. If you wanted to spend, let's say, if you wanted a higher speed, all you have to do is to increase the duty cycle. So let's go for 25%. This means that 3/4 of the time you'll be spending it at high, and 1/4 of the period it will be spent at low. Hence, you're gonna have a 75% of your maximum voltage. Fair enough? And this is it. This is what you need to know about your PWM. So the period is the different highs, rising edge, and the duty cycle, right? So this is the high, so the logical one. So it is a percentage. I've explained the case of the DC motor as an example, and if we use the example for the servo motor now, and we can conclude that this schematic belongs to a servo motor from the angles that we have here. So you can see that if you define a duty cycle of, let's say, 20%, whatever the data sheet tells you what is the needed duty cycle in order to have a particular angle, so you're going to use it. So as an example, let's say that this is 25%, duty cycle of 25%, this means that your angle will be 0. Let's say that this is I don't know, 75% or no, 50%, let's say that. So it should represent a 90-degree angle here, and then let's say a 75% or something like that. This would represent a 180-degree. Fair enough? All right. So to have a concrete example, and again, whenever you're gonna control a non-analog actuator, in the sense of it has more than a binary value on and off, well, you're going to use a PWM from now on, right? So in Atmega 328P microcontrollers, well, the question is, what pins are connected to the PWM module? So what pins are enabled to be used as PWM ports for PWM signals? Right? You're going to check those out in more details in the tutorial. And the idea is how to deal with the frequencies, and we've seen from the watchdog timer that we use a particular component, digital component, when it comes to getting different frequencies from one general oscillator or clock. Yes, so it is a prescaler, also known as a frequency divider. Alright, and for this particular microcontroller, if I'm not mistaken, we have 3 different modes, and of course you refer to the datasheet in order to know which one to use and how to use them, and it all goes down to programming a relative or the concerned registers with the proper ones and zeros. You have a whole tutorial on that particular PWM topic. Alright, when it comes to the Arduino, let's imagine that we're controlling the servo, so we're going to use the function that is called analog write. So there's a dedicated function. Whenever you call it, well, you'll be controlling, you'll be generating a PWM signal in order to control, let's say, a servo. And of course, because you need to, with PWM, you need to specify the duty cycle. Well, the function should have at least an attribute that is the percentage of your duty cycles. So for instance, if you're trying to have a duty cycle of 0%, well, you're going to call the function analog write with 0. If you wanted to have a 50% duty cycle, well, you're going to call it with the value of 127. Alright, and you can see these are relative to some binary scheme. I'll let you think about it yourself. Alright, the last thing, and this is the infamous Arduino Uno board that we've seen a couple of times in my class. And according to the datasheet, well, they're telling you that some pins are connected to the, they are used for PWMs. So you can see it here, PWM with this weird sig here. Kind of look like a weird mustache, but anyways, you can see that this is the PWM pin, PWM, 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 PWM. All right. And they're telling you that 5 and 6, so those 2 pins here, they are with the 980 hertz frequency, and the others they operate at 420. for 90 hertz frequency. All right. Um, so whenever you're gonna control a motor and generate the PW pin, you should check the frequency of the motor, or if you can have smaller frequencies based on those ones, always refer to your datasheet, right? And connect them to the proper pin. Right? So let's wrap it up with an example, a real life example, and you'll be doing a lot of that in your project, that's for sure. So we're seeing the description of the analog write function. So all you have to do is go and check which board do you have. In case of a Nuno, you're seeing what are the different PWM pins and the available frequencies that you can work with. And by the way, why do you have different frequencies? For what reason? The answer is for your actuators, they operate on different frequencies as well, so they need to be compatible. So in order to get the proper frequency to make sure that your actuator is not heating up, or it's not it doesn't lag or jitter, right? So you need to have the appropriate frequency. And then, so let's assume that we're using a Nuno here, and we're gonna connect to the proper pins depending on the frequency that we want, or maybe some other frequency that could be obtained from those frequencies. And the idea is to see the syntax. So the analog write, it takes two attributes here. The first one is naturally the pin where you're expecting to output your PWM signal, and then the actual value that you want to put. And you can remember from the previous slides that the value could be anything between 0 and 255, plus you have it here. So the value is the duty cycle that goes from 0, so always off, so no voltage at all, or the full voltage, so full speed in case of a motor, that is represented by 255. Alright, perfect. So let's see an example here. So we're gonna try and study the schematic. So apparently we're using a LAD, push down resistor, right? And then you can see that the LAD is connected to a pin that has the PWM signal here. Whoop, what? A LAD? I thought a LAD was only on and off. So why would I connect it to a PWM signal? Well, the answer is maybe we don't want it to be full bright or off. Maybe we want to control the brightness of the LED. So let's do that. Alright, so it's connected physically to pin number 6, and it is a PWM signal, so we're good. So yeah, we've defined this particular pin, we call it LED pin, and as in each and every Arduino program that you'll be doing, you should have two functions, and those functions are the setup function and the loop. How many times the setup function is called? Only once. And how many times the loop function is called? Well, the loop is a perpetual one, so it goes on as long as your system is under power. Alright, so first and more importantly, I'm using a general input output port here, pin, right? So basically I need to define whether I need to define its direction, whether it's an in or an out. So basically here we're defining our pin number 6 to be an output, of course, because I'm connecting an actuator to it. Fair enough. And that's it for the setup. This is what I need to do. Alright, let's try and do that. How would I control the brightness? Let's say I wanted the brightness to start from 0 and keeps on progressing to full brightness, and then I want it to go back to 0 again, over and over again. So let's think about it for a second. Alright, so in the loop, all I need to do is create some kind of for loop here that goes between 0 and 255. So remember, 0 means that my duty cycle is 0%, and 255 my duty cycle is full 100%, right? So I'm gonna go step by step from 0 all the way up to a full duty cycle. Alright, so this is what I'm doing. So I'm spitting out the value of I, right? So I go from a completely shut off LED, and bit by bit I want to go to a full brightness here, and I'm telling you I want to go back to the fully off LED. So what should I do next? Alright, so it's a delay, so we can perceive it as human beings that something's happening over there. And then I'm gonna do the opposite, so I'm gonna go from 255 this time all the way down to 0, almost to 0, right? And I'm gonna spit it out. I'm gonna delay again, and that's it. So how would my system behave here? Well, once I flashed my program, the LED is going to go from a complete off bit by bit all the way up to a complete bright LED, and then all the way down to be shut off completely. Alright, thanks for watching, and this is the end of the hardware aspect of the embedded systems that we're having together. Starting next lecture, we're gonna tackle more the software layers, and especially the real-time operating system layer.